Question: if X is the dimensionality of a free electron gas, the energy E dependency of density of states is given by e power x divided by 2 minus y, where y is. So in this question, they have given that density of states G of E is proportional to e power x divided by 2 minus y, and they have given x is the dimensionality of a free electron gas, and they have asked us to find what is the value of this y. So we have studied for one dimension density of states is proportional to e power minus 1 by 2, and for two dimension density of states is proportional to e, that is it's not 0, it is e power 1 here. And for three-dimensional density of states is proportional to e power half. So from this 3 we can write as a general formula for density of states as g of e is proportional to x e power x divided by 2 minus 1. Here x is the dimension. So if we substitute x value here, x value is 1, and for here x value is equal to 2, and here x value is equal to 3. So this is the general form that is given in the question. Now by comparing these two, we can write y value is nothing but 1. This is plus 1. So y value is equal to plus 1. Consider an infinitely long solenoid with n turns per unit length. Radius r carrying a current I of t is equal to alpha cos omega t, where alpha is a constant and omega is the angular frequency. The magnitude of electric field at the surface of the solenoid is. So in this question they have given a infinite long solenoid, and it is having a n number of turns in it. And number of turns per unit length is L, and radius of the solenoid is given as R, and this solenoid carries a current of I, that is I of t is equal to alpha cos omega t. They have asked us to find what is the magnitude of electric field at the surface of the solenoid. So the electric field can be found out by using the Faraday's law. According to Faraday's law, when there is a change in magnetic field is there, electric field will be induced in it. So we can write closed integral of E vector dot dl is equal to minus of dou phi by dou t. In terms of magnetic field, it is minus integral of dou b by dou t dot dA. So magnetic field, we know that for a solenoid it is mu naught n into I. Now substitute it here. So we will be getting minus integral of dou by dou t mu naught n into I dot dA. So in the left hand side, integral or closed integral of dl vector is nothing but the 2 pi r. Now in case of right hand side, minus mu naught n dou I by dou t integral of dA. Integral of dA is an area element, so it will be getting pi r square. So in left hand side we have E into 2 pi r, and in right hand side it is minus mu naught n. Substitute the value of I, you will be getting dou by dou t of alpha cos omega t into pi r square. This pi and this pi will get cancels off, and here r square also 1 r will be getting cancels off. So left hand side we have 2e, that is equal to mu naught n I r. So differentiating alpha cos omega t, we will be getting minus alpha sine omega t into omega. So this minus will get cancels off with this. So we'll be getting plus mu naught n r alpha sine omega t into omega. That is nothing but electric field is equal to half mu naught n r alpha omega sine omega t. So answer is option A. Question: a constant and uniform magnetic field B vector is equal to B naught K cap pervades all space. Which one of the following is the correct choice for the vector potential in Coulomb gauge? Option A, minus B naught x plus y I cap. Option B, B naught x plus y j cap. Option C, B naught x j cap. Option D, 1 minus 1 by 2 B naught x I cap minus y j cap. So in this question we have to find which among these four vector potential satisfies the Coulomb gauge condition. So the Coulomb-Gauss condition is del dot A vector is equal to 0. We have to take each of the option and find which satisfies this condition. We will take the option C, that is B naught x j cap, and find whether it is satisfies or not. So del vector dot A vector is equal to dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap dot B naught x j cap. So here by dot producting of del and A vector gives dou by dou y of B naught x. As it doesn't have any y term in it, the partial differentiation with respect to y will be 0. So for option C, the Coulomb-Gauss condition is satisfied. Therefore, answer is option C. Question: consider a long straight wire having radius A and resistance per unit length R carries a current I. The magnitude and direction of pointing vector on the surface of the wire is. So in the question, they have taken a long straight wire that carries a current of I. They have asked us to find what is the direction and magnitude of the pointing vector. So the pointing vector is given by the formula 1 divided by mu naught E vector cross B vector. We have to find what is the value of E and B. Substituting here, we can find the magnitude and direction. First, we will find the magnetic field. The magnetic field for a long straight wire that carries a current I is given by B vector is equal to mu naught I divided by 2 pi A into x cap. X cap denotes the direction of propagation of the magnetic field. So in the similar way, the electric field E vector is equal to rho J vector into y cap. Y cap denotes the direction of propagation of the electric field. For rho, we can write R A divided by L J vector into y cap. So in the question, they have given R divided by L is equal to R. That is resistance per unit length is equal to R. And we have studied the current density is equal to I divided by A. Now substitute these two in E vector. You will be getting E vector is equal to R A into I divided by A y cap. So R will get cancels off. We will be getting E vector is equal to R I y cap. Now we have found what is the electric field and magnetic field. Substitute in pointing vector to get the value. S vector is equal to 1 by mu naught R I y cap cross mu naught I divided by 2 pi A x cap, that is equal to r I square divided by 2 pi a y cap cross x cap. So the answer for y cap cross x cap is nothing but minus of z cap. So we will be getting minus r I square divided by 2 pi a z cap. So the pointing vector s is equal to minus I square r divided by 2 pi a into z cap. So answer C and D is incorrect. Answer is either A or B. This negative sign denotes that the pointing vector is pointing in the inward direction. Question: the energy dispersion for electrons in one-dimensional lattice with lattice space A is given by E of k is equal to E naught 1 by 2 W cos Ka, where W and E naught are constants. The effective mass of the electron near the bottom of the band is. So in the question, they have asked us to find what is the effective mass of the electron near the bottom of the band, and they have given the energy dispersion of the electron also. So the effective mass of the electron m star is given by the formula h cross square divided by d square E by dk square. So we have to find what is the value of E with second derivative of E with respect to k. So in the question they have given E as E naught minus 1 by 2 W cos kx. The second derivative of E with respect to k is W divided by 2 A square cos Ka. Therefore, substitute the value in m star. We will be getting h cross square divided by w by 2 a square cos ka. In the question, they have asked us to find what is the effective mass near the bottom of the band. Where k goes to 0, the value of cos ka will be equal to 1. Therefore, by substituting it here, we will be getting m star as h cross square divided by w by 2a square, that is 2h cross square divided by wa square. So answer is option A.
In the description box, you can find the link for GATE Physics 2019 and 2020 solution. Please share and subscribe the channel. If you have any queries, write in the comment section.